Welcome back to ECE 442-542. In Part C of Lecture 6.3, 6.3 is PI controller with examples. We're learning a little bit about the PI control. In B, we learned the structure. Now what we want to do is talk about how we can combine that PI controller with root locus, and to help us with that combination of those two concepts, let's use this segment of lecture 6.3 to get us better ready to work with these root locus rules. So we'll first talk about the origin of the root locus. That's really just parameterizing the characteristic equation so that it's a function of this adjustable parameter k, and then we will state the root locus rules. Rule number 1, where do our root locus branches begin and end? That's rule number 1. They begin on the open loop poles, they end on the finite zeros. If we have infinite zeros, some of those branches will go off to infinity in the complex z-plane. Beginning and ending, that's rule number 1. Rule number 2, what segments along the real axis actually belong to the root locus? In our system, we typically will have poles and zeros. They could even be on or off the real line, but this rule really only worries about the poles and zeros on the real axis. We've now separated the real axis into, think of this as a long piece of bread. That's the blue highlight. That's the real axis. We've now, with those 3 poles and 1 zero, we've cut this bread into 4. We've had 4 cuts. We now have a piece of bread here. There's 1, 2, 3, 4, and 5 pieces of that bread. Those are now 5 different line segments. We want to know which of those segments belong to the root locus, and we will learn that the segments that belong to the root locus are those segments that have an odd number of poles and zeros to the right. If we looked at this particular point, there's no poles and zeros to the right, so that line segment from wherever that is to positive infinity does not belong to the root locus. This segment does, because every point here has 1 pole to its right. How about there? Well, now we have an even number of poles to our right, so that segment of the real line doesn't belong on the root locus. This segment does, because we have 3 poles and zeros. We have 1 zero and 2 poles. We have an odd number of poles and zeros to our right. That segment now belongs on the root locus diagram, and any point to the left of that leftmost pole does not live on the root locus, because there's an even number of poles and zeros to the right of that point. And then we will talk about breakaway and reentry points on the real axis. That's rule number 3. And when do we have breakaway and reentry? Well, when we have multiple branches on the same segment of our real axis. Here we have a branch, and here we have a branch. We have 2 branches of our root locus on the same line segment. Those 2 cannot terminate. They actually have to break away from the real axis. We want to know where do they, and those 2 lines should have been exactly at the same point on the real line. Where do they break away? And we could have a reentry point. In this case, we do not. But we could talk about, we have breakaway and reentry points on the real axis. That's rule number 3. And we will actually illustrate rule number 3 with an example. And this is our lead-in line to a joke: 2 poles to the right of 1 zero. Well, that hopefully you'll just start remembering that. 2 poles to the right of 1, 0. By that I mean we have a diagram here. There's our z-plane. We have 2 poles, and those live to the right of 1, 0. When we have that structure of poles and zeros, we can now fairly quickly sketch the root locus diagram associated with that pattern of poles and zeros. And we'll illustrate that, and that's actually an application of rule number 3, because in fact we have a breakaway between those 2 poles, and we have a re-entry to the left of that 0. And based on rule number 1, we know one of those branches will terminate at the 0, the other branch will move off to negative infinity, and somehow we have to break away here and end up coming back in to that 0, and we'll find that that's actually a circle. That's not a very good circle. The radius of that circle is from the circle's origin or center, which is that circle is centered at the 0. So like I said, that's a terrible circle, but that radius should be the same all the way around that circle. That's now how we will illustrate rule number 3, and hopefully that will become a little bit more clear as we go through. The origins, or the beginning, of the root locus. We were trying to now understand how do these values of z that satisfy this characteristic equation, where are they on the complex z-plane? Those values of z that satisfy 1 plus k bar g bar equal to 0 are our closed loop poles. It would be nice to know, oh, can we for each value of k bar find a new set of values z? Yes, we can, that satisfy that, and the collection of those values or locations in the complex z-plane create the root locus diagram. Those are our root loci. Those are the roots. Those are the locus of roots that result by changing k bar from 0 to infinity and finding for each of those values of k bar from 0 to infinity what the values of z are that cause this particular expression to be true. 1 plus k bar g bar z equal to 0. If g bar has a numerator polynomial n and a denominator polynomial d, we can convert this 1 plus k bar g bar into this rational expression of a polynomial in the numerator, d plus k bar n over d. Well, when is that equal to 0? That will equal 0 when the numerator is equal to 0. And what we are now looking at is we're saying as we let k bar go from 0 to infinity, we have different values of z that satisfy that equation. Hopefully you can see that when k bar is equal to 0, the values of z that cause that to be true are the values of z that allow d of z to be equal to 0. That's when k bar is equal to 0. As k bar gets big, as k bar gets really, really big, as k bar goes off to infinity, then the second term in that left side is going to dominate, and that will then correspond to values of z that cause n of z to equal 0. And now, as k bar varies from 0 to infinity, between those two extremes, the values of z that cause that to vanish will produce these root locus diagrams. The numerator of 1 plus k bar g bar is d plus k bar n, and that's the numerator of t sub c of z's denominator. That's our closed loop poles, and that's where these root locus rules are derived from, or they originate from this condition. D plus k bar n is equal to 0. what's the first rule? So here are the first three. In this class we will have 5 root locus rules. In Unit 6 we will focus or concentrate on the first 3 rules. Rule 1 gives us the beginning and ending of the root locus branches. And here's the statement of root locus rule number 1. The root locus branches. And how many branches of the root locus do we have? We have as many branches as there are roots of d of z. If d of z is now 5th order, we would have 5 branches. We would have 5 beginning locations of our root locus diagram. We start at the poles. The root locus branches begin at our open loop poles. And the open loop poles are those values of z that cause d of z to equal 0. In the finite complex z-plane, those branches, let's say we had 5, those 5 branches, some of those end on open loop zeros. Our open loop zeros are the values of n of z, they're the values of z that cause n of z to vanish. And those occur as k goes to infinity. Obviously, we may not always have as many zeros, finite zeros, as we have poles. That difference, we call it many different things. We'll call it the pole zero excess. We'll call it the number of zeros at infinity. That number, the number of zeros at infinity, are the branches of our root locus that go off to infinity. So some of those branches go off to infinity. Let's say we had 5 poles and 2 finite zeros. Then 5 of those branches of the root locus would approach those 2 finite zeros. So 2 branches would terminate in our finite dimensional z-plane. 3 of those branches would go off to infinity. And the number of branches that go off to infinity is equal to the pole zero excess, or the zeros at infinity. That's rule number 1. Rule number 2. The real axis segments, and remember our bread, this is rule number 2, is dealing with our bread and cutting it up into segments. The real axis is being divided into segments based on where our poles and zeros are positioned on the real axis. The real axis segments that belong to the real axis, the real axis segments that belong to the root locus are determined by rule number 2. And this really is a result of the phase angle condition, or all values of z on the root locus have to possess an angle of minus 180 degrees. And here this is for k being non-negative, or k being, let's say, just positive. Real axis segments in the z-plane belong to the root locus if an odd number of poles and zeros lie to the right of the real axis segment. In our case, we could quickly sort of illustrate many different scenarios. Suppose that you now have those 2 poles. You now have 3 real axis segments. One to the right of the right pole, one segment in between those 2 poles, and another segment to the left of the leftmost pole. Of those 3 segments, which segments belong to the root locus? Well, by rule number 2, it says the real axis segments in the z-plane belong to the root locus if an odd number of poles and zeros lie to the right. Any segment here has that odd number, or one pole to its right. That's the only segment of the 3 for this pattern of poles and zeros that belongs to the root locus. If we had another pattern that looked something like that of poles and zeros, now we simply stand at each location. We stand here and we say, looking to the right, do I see any poles and zeros? No. So that segment between that rightmost pole and plus infinity does not belong to the root locus. If I'm standing there, now any place here, I now see one pole, so that segment, real line segment, belongs to the root locus. What about any point here between the 0 and the pole to the left? Now I have an even number of poles and zeros. I have one pole and 1 0. 1 plus 1 is 2. Last time I checked, that's even. So points between the 0 and that leftmost pole do not belong to the root locus. Any point here does belong to the root locus, because any point wherever you're standing here, you look to your right and you see an odd number of poles and zeros. We've now found which real axis line segments belong to the root locus based on rule number 2. The third rule concerns breakaway and reentry points, and you may not have these. This rule may not apply depending on your particular pole zero pattern. But we can have breakaway and reentry points, and you could have breakaway and no reentry. You could have simply reentry and no breakaway. But breakaway points and reentry points on the real line are locations of relative maximum gain values of k. Those are the breakaway points. And relative minimum gain values of k. Those are the reentry points, respectively. Here's an example. Again, like I said, this is our lead-in line to our joke. 2 real poles to the right of a 0. You can see, hopefully, the 2 x's. Those are our poles. So the very first thing you want to do when you're sketching a root locus is immediately factor your transfer function into pole and 0 factors. You plot your poles as x's in the complex z-plane, and you plot your zeros as open circles. Here we have 2 poles and a 0, and it just so happens that those 2 poles lie to the right of that 0, and all 3 are on the real axis. How many branches of root locus do we have? How many open loop poles do we have? How many x's do you see on the diagram? You have 2 x's, you have 2 open loop poles, you have 2 root locus branches. There's actually, although it's just one line segment, you have 2 branches of your root locus between those 2 poles. You can use rule 1 to figure out that this segment belongs to the root locus, and this real axis segment belongs to the root locus. That's rule number 2. And I'm going to fail to erase that highlight without tearing everything up. So now I've torn up my real line, but there's my real line. I now have, from rule 2, figured out which segments belong, which real axis segments belong to the root locus. I now want to know, well, if I have 2 branches, I have this branch and I have that branch. I have 2 branches. One branch starts on one pole, the other branch starts on the other. Those 2 branches cannot terminate by running into each other. They have to go somewhere, and they are going to bounce off the real axis, and that's called a breakaway. That's the B. Z sub B is our breakaway point, and that's a relative maximum of the gain K. Remember what we're doing. We are finding the values of Z in the complex plane that satisfy 1 plus K bar G bar equal to 0. Those values of Z are represented by the red branches on the Z-plane. We have 2 poles in this 1 plus K bar G bar expression. They start, the root locus starts on the poles, the open loop poles, which are the roots of D of Z. That's the x's. As we adjust the gain K from 0 up to infinity, we now move around the complex z-plane on these branches. As we adjust the gain k, this pole is going to move to the left. As we adjust the gain k from 0, this pole is going to move to the right. At some gain k, those two are going to be real and equal values of our closed loop poles right on the real axis. If we adjust the gain higher than that k value that made them real and equal, then one of these poles is going to go here, and the other pole, the other branch, closed loop pole, is going to go there. Now, we're not going to worry so much about why they move in a circle just yet, but we do know that based on the phase angle condition, we have nice symmetry conditions. But we also know from rule number 1 that we have these branches terminating on finite zeros. We have one finite zero, and we know that we have this line segment from the left of that zero all the way to minus infinity. It lives on the root locus. This particular branch is going to go here, and let's just, I don't know which one will, but let's just assume that one ventures in to the finite zero. The other branch of our root locus will come around, and it will then go off to infinity. And that's how we then will sketch the root locus. For two real poles to the right of a zero, it has this nice structural characteristic. The two poles come together and meet between each other. They actually break away at a value that's the geometric mean between those two pole locations and the zero. And that geometric mean, that distance, that value, that numerical value, that r, is the radius of this circle, and the circle's radius is centered at the zero. There's a distance, I'm calling it little l sub 1, between the 0 and the first pole. There's another distance, I'm calling that l sub 2, between the 0 and the second pole. The geometric mean is the square root of the product of those two. So now we're multiplying and square rooting, whereas the arithmetic mean is we're adding and dividing by the number of values that we're taking the average of. Here, we're multiplying two numbers, and we're taking the nth root, the second root, the square root of their product. That's the geometric mean. Now, what we do know as well is that particular two poles and a zero has as a transfer function this structure. We know from our root locus origins that the magnitude condition k g of z is equal to 1. And from that, we can now solve for the gain k, and this k is going to vary from 0 to infinity for different values of z in the complex plane, and we will calculate this k for z values on this red locus. So we could now calculate a z value for that particular point. Let me say that box. And that's going to then correspond to another box there. So for a given k, we will have our two closed loop poles at those box locations. We crank up the gain a little bit more, and now we get it to a value of k that gives us two real equal poles. And now I'm labeling those as those triangles. We adjust the gain k a little bit more, and now we have our complex poles at these cloud locations, and those should have been complex conjugate. So that should be directly underneath that last cloud. And you crank it up even more, and as you crank it more and more, we will eventually get one going off to minus infinity and the other one approaching that finite zero. Let's actually work through this breakaway and reentry point with a particular example, numerical example. Above, I just illustrated it. I'm losing my voice. Maybe we won't do this. But now let's go ahead and work through an example of two poles to the right of a zero. The example that I'm going to use, let's say that our zero is right at the origin, and let's let one pole be at 1 and another pole be at 2. Just from that, you should be able to start sketching a root locus. You have a 0 at the origin, you have a pole at 1 and another pole at 2. That's now the beginning and ending locations of your root locus diagram. From rule number 2, which of these, how many line segments do we have identified now by this pole 0 pattern? How many places have we cut the bread? How many places have we actually separated into line segments our real line? Hopefully you see that we've cut the bread there, there, and there, and we have a piece there, a piece there, a piece there. We have 4 different line segments have now been identified by that pole 0 pattern. Which of those line segments live on the root locus? Well, now we look and say which of these segments have an odd number of poles and zeros to the right, and we now know that those are the line segments that belong to the root locus. How many branches do we have of our root locus? It's not those 2, it's actually the number of branches is equal to the number of poles. We have 2 poles, so we have a branch and another branch, and those 2 branches are going to collide. What we want to know is where do they break away, where do they leave the real line. We also have 2 branches over here on the left, although they're just shown by one line segment, but we have one branch that's going to terminate at the 0. The other branch is going off to minus infinity. What we want to know is how do these break away here and one come over here and the other one break away and go over there. We want to now determine what's the value of z where it breaks away and what's the value of z where it re-enters. Can we compute those for this numerical example? We know from our magnitude condition that in fact kg of z, the magnitude of that equals 1. Again, this is coming because we have 1 plus kg of z equaling 0. We solve or subtract 1 from both sides. And now we have 2 conditions on g. The magnitude of kg has to be 1, and the phase of kg has to be minus 180 degrees. Let's now work with the magnitude condition. We now know that k, z over z minus 1, z minus 2 is equal to 1. We can solve that for k, and k we're going to have be positive. So now the expression for k is now z minus 1, z minus 2 all over z. And to make this work for our analysis, let's just take the magnitude of what's inside all of that mess we now have a quotient of the numerator product, that's the pole factors, z minus 1 in our original system, times z minus 2, divided by the numerator factors, which in this case are just z. Now, we said that the breakaway from rule number 3, the breakaway and the reentry points occur at relative max and relative min. When I say relative max and relative min, what are you thinking? What math class did you talk about relative max and relative min? That's right. Way back in your first semester of calculus, you learned how to find relative max and relative min. We now want to know, how do we find that? Well, if we take the derivative, and if the derivative of this functional expression is equal to 0, then we are experiencing a relative maximum or a relative minimum. If we now differentiate that expression inside the absolute value sign, let's now just do that. We have the, well, before we do that, let's go ahead and multiply this out so that we just have a polynomial in z. This is z squared minus 3z plus 2. That's now our numerator factor. Our denominator factor in our gain k expression is just z. We now have a quotient. We can find the derivative of that quotient. We now take the derivative of the numerator, which is 2z minus 3, times the denominator minus the numerator, that's a z squared minus 3z plus 2, times the derivative of the denominator with respect to z. dz is just 1. And that's divided by z squared. And again, we will want to take the magnitude of that, but for now, let's not worry so much about that. We want, well, let's go ahead and say that. We now want the magnitude of that to equal 0. We can make that happen if we make the numerator of that expression equal 0. If we look at the numerator, let's say of this dk dz expression, that's now 2z squared, distributing that z across those two terms, minus 3z minus z squared plus 3z minus 2 is equal to 0. We have some cleaning up to do, and now we see that 2z squared minus z squared, we end up with z squared minus 2 is equal to 0. We're looking for values of z that cause that derivative to equal 0. In this case, that's when z squared is equal to 2, or when z is equal to plus and minus the square root of 2. Or that's now z is equal to plus and minus 1.414, and those values of z correspond to our relative minimum, maybe I should say relative maximum, and our relative minimum. Of what? Of our k expression. And those relative max and relative min of our k expression tell us where we have a breakaway and a reentry. This is now a relative max, and we've now just found that z sub b is plus 1.414. That's the square root of 2. This relative min is our reentry, and that's now z sub r is equal to minus 1.414. So we re-enter the real axis at minus 1.414. We break away at plus 1.414, and look at what the square root of 2 actually is. Well, or another way of thinking of that, now this is a radius determined by the breakaway and the reentry points, and that radius has a value of square root of 2. And what is that radius? That radius, if we look at it, is actually the square root of this length, which is 1, times this second length from the 0 to the second pole, L2. So this is now the square root of 1 times 2, or the square root of 2. And that is how we can quickly sketch. We know from the phase angle condition, which says that the phase of G is equal to minus 180 degrees, now allows us to have this nice symmetry of the root locus diagram. In fact, this now is red. As we crank up the gain k, we move on that circle. It's a circle of radius, square root of 2. And now we know how to sketch root loci for this special case of 2 poles to the right of a 0. We just verified that for a particular numerical plant of z over z minus 1 times z minus 2. 2 poles to the right of a 0. You could, if you didn't want to do all of this differentiation, you could have actually looked at this expression for k. K was now z minus 1, z minus 2 over z. If somebody said, you know what, I have a calculator, maybe I can now just compute what k is for different values of z, because I know that between 1 and 2 I have to experience a relative maximum. Remember, we're adjusting this knob k from 0 to infinity, and as I crank up the gain k, it's only going to get me to where those two collide, and then after that point I'm going to leave the real line. So I'm going to have a relative maximum value of k between 1 and 2. Somebody now says, you know what, I don't want to do all that differentiation, I've forgotten my quotient rule. Let me just evaluate this expression for k at different values of z. Suppose now you evaluate it for z equal to 1.5. You will hopefully find that now becomes 0.167. Then you say, oh, well, let me go a little bit smaller towards the origin, 1.45. Now I'm at a gain of 0.1707. So in fact, this is really sort of saying that I'm not breaking away midway between 1 and 2, which is at 1.5. It looks like my gain is increasing as I get to the left of 1.5. At 1.45, my gain k is bigger. And so now what happens if I get a little bit smaller? What if I look at 1.42? Well, now my magnitude k is 0.172. I'm still getting bigger, it looks like. Or have I gone through the relative max? Let me look at 1.41. I know the answer, so that's, now I'm at 0.172 again. So my relative max is probably occurring between 1.42 and 1.41, and I calculated that numerically from just knowing my expression for k. And I could now say, well, let me see. 1.40, that's 0.171. Now I'm going down, I'm decreasing in k. So I hit my relative maximum of k between 1.41 and 1.42, or that's now this square root of 2, 1.414, etc. That's now how you could also numerically calculate this breakaway point from your magnitude expression for k.